In this video here, we're going to take a look at exam revision for trigonometry and modelling. So for this video then, all we're going to do here is work for a few exam style questions based on trigonometry and modelling. And as you can see then, this will cover the following topics here. So what do we have for this video then? Well, we have the addition formulae as well as the double angle formulae. We then look at solving trig equations involving the double angle formulae. We also have the harmonic formulae, proving trig identities, and then finally modelling with trig functions. So as always here, what I would recommend then is that you pause the video and have a quick look at the questions as they appear, and then just double check that your solution matches what we get on the screen. So that should give us everything that we need here to get started. Let's begin now then with question 1. Alright, so let's just get started here then with question 1. So for this question here, let's begin with part A. So for part A then, all we want to do here is show that sine A minus cos A all squared is identical to 1 minus sine of 2A. So let's begin with here then, we have sine A minus cos A squared. Okay, so this here then is just the same as sine A minus cos A times by itself again. So sine A minus cos A, like so there. Okay, and what we can do here then is just expand these double brackets, right? Using file or any method that you're familiar with, like expanding double brackets, but that should hopefully be, at this point, very straightforward. So if we do that here then, what do we get? So sine A times sine A, that gives me sine squared A. Get sine squared A there. We then have sine A times minus cos A. We get minus sine A cos A, like so. We then do the same here, so minus cos A times sine A again. We get minus sine A cos A, like so. And then finally minus cos A times by minus cos A here. That gives us plus, so just be careful with your signs here. So plus cos squared A. Okay. Well, if we just notice here then, if we write this as sine squared A plus cos squared A, just bringing my first term and my last term together here, you should be aware then that sine squared A plus cos squared A is just equal to 1. Now I've got minus sine A cos A minus another sine A cos A, we have minus 2 sine A cos A. Like so. So as we mentioned then, right, sine squared A plus cos squared A, that's just 1. So what I've got here then is 1 minus 2 sine A cos A. Like so. And what you need to recognize here then, that 2 sine A cos A is just the same as sine of 2A. It's one of our double angle identities, right? So in that case then, what I've got here is 1 minus sine of 2A. We don't need the brackets here, so let me just get rid of the brackets. They're redundant. So in that case, then we get 1 minus sine of 2A, exactly as required. Okay, so as required there, and that gives us the solution to part A. And now for the second part of this question here, then part B, it says, hence find the exact value of, so we have sine of pi over 6 minus cos of pi over 6 all squared. Now, given that part B then starts with the hence here, what that means then is we're going to use the answer from part A to help us answer part B. So for part B, let's just do that over here. So we have sine, I'll do it in brackets as well. So sine of pi over 6 minus cos of pi over 6 all squared. Okay. So how does this here then connect to what we had in part A? Well, the only difference here then is our A then is pi over 6, right? So it's sine of A, where A is pi over 6, minus cos of A, where again, A is pi over 6. And we know then that this expression here is identical to 1 minus sine of 2A. So this expression here then is identical to 1 minus sine of 2A. So A here was pi over 6, so 2A then would be 2 lots of pi over 6, which is just the same as pi over 3. So what we get here then is 1 minus sine of pi over 3. Well, in that case then, what we get here is 1 minus root 3 over 2. So don't forget then, that we want to give the answer here as an exact value. So keep everything exact here as we go. And then finally, if we get this over a common denominator here, then what would we get? So I get 2 minus root 3 all over 2. We get 2 minus root 3 there over 2. And there we have it. So that gives us the exact value then of this expression here. So hopefully, nice and straightforward there just to get us started. And that gives us the solution to question 1. So we now move on to the next question here then, where we have question 2. And for the first part of question 2 here then, all we want to do is use the double angle formulae to prove this trigonometric identity here. So for part A then, let's just begin here then by writing down the left-hand side, because clearly what we want to do then is start with the left-hand side. As the question suggests, use the double angle formulae, and then hopefully with a little bit of manipulation here, we should obtain the right-hand side. Okay? We've got 1 minus cos 2x, and that's all over 1 plus cos 2x. Okay? So, as the question suggests, right, we need to use the double angle formulae here. So, we've got cos 2xm. Now, you should be aware then that cos 2x here is identical to cos squared x minus sine squared x. Okay? Now, I'll do this in a different color here. If I substitute in this result here, or this identity here, into minus cos 2x and plus cos 2x, that's not going to be much use, right? It's not going to lead to anything useful. So what we need to do here then is use the other two identities here then for cos 2x. So by using sine squared x plus cos squared x equals 1, we can substitute here by rearranging and substituting in for cos squared x or sine squared x, and this leads to 2 further identities here for cos 2x. So you should be aware then that cos 2x is also identical to, so we get 1 minus 2 sine squared x. And then for the final identity here, let's do that in red. It's also identical to 2 cos squared x minus 1. Okay? So what I'm going to do here then is substitute this identity here into my numerator for cos 2x, or minus cos 2x. And I'm going to substitute this identity here into my denominator for cos 2x. Okay? If we do that here then, what would we get? We get 1 minus, and let me do this here in the respective color, so light blue then. We get 1 minus 2 sine squared x. Okay, like so. And this here then is all over. That's all over 1 plus cos 2x. And for this cos 2x here, we substitute in this identity here. And again, let's use the respective color. I get 1 plus 2 cos squared x minus 1. Okay? So now if we simplify here then, what would we get? Well, 1 minus 1 here, they just cancel, like so. So I've now got minus 2 sine squared x. That just gives us 2 sine squared x there. Hopefully nice and straightforward there. And this here then is all over. So again, the ones just cancel here. So 1 minus 1, they just cancel. What we get left with here then is 2 cos squared x. Like so. Well, clearly the 2's just cancel here. So they just cancel. And what we get left with here then is sine squared x all over cos squared x. Okay, so sine squared x over cos squared x. And you should be aware then that sine squared x over cos squared x would just give us tan squared x exactly as we require, right? So as required there. So this here then is equal to the right hand side. And there we have it, proof complete. So as required there. So as required, and that gives us the solution to part A. So now for the second part of this question here, it says hence or otherwise solve for x between 0 and 2 pi the following equation here. So just notice then, the left-hand side of our equation here is identical to the left-hand side of our trig identity here, right? So what that means then is I can replace my left-hand side here with the right-hand side here. Okay, and that's why it's a hence part of the question, because we're going to use the answer from part A to help us answer part B. So for part B then, let's do that over here. We can replace then the left-hand side here with tan squared x. So what I've got then is tan squared x. So tan squared x is equal to 1. So clearly the first thing that I need to do here then is take the square root of both sides. So in that case then, what we get here is tan x is equal to plus or minus 1. Okay, now that's important. Don't forget the negative solution here as well. A common mistake is just take the positive solution. So from here then, this gives us two solutions. So tan x is equal to 1. And in that case, then we obtain x here. So x is equal to tan inverse of 1, or arctan of 1, whichever way you prefer to denote that. We'll come back to the actual solution in a moment. What we've also got here then is tan x is equal to minus 1. Okay, and again, we can just obtain x here by taking tan inverse of both sides. So tan inverse then of minus 1. Okay. So don't forget then, we are working in radians here. If you're going to use your calculator, just ensure then that your calculator is in radians mode as opposed to degrees mode. Okay. So x is equal to tan inverse of 1 here. So what this gives me then is pi over 4. Okay. So all I've done here then is just put tan inverse of 1 into my calculator, and that gives me pi over 4. So now to obtain the full solutions here then to this equation, all I'm going to do here is use a cast diagram. But if you do prefer a graphical approach, that's also fine as well. But personally, I prefer the cast diagram to a graphical approach. So for my cast diagram here, let's just do that here. Doesn't have to be perfect, by the way. Something like this here will do. So bottom right then is for cosine, top right is for all trig functions, top left is for sine, and bottom left here is for tan. Okay? So this solution here of pi over 4, that corresponds to this angle here. Okay? So that's pi over 4 there. Now, we do also have a second solution here in this quadrant. Okay? So this angle here is also pi over 4. But what we want to know here then is what is the angle that's formed when we go from this line here, essentially the x-axis, all the way around until we meet this line here. Okay? Well, hopefully it's clear to see then that this solution here, this second solution anyway, again, let me just do it in red, would be pi, because we go from here to here, which is just 108 degrees, or pi radians. We've got pi then, plus this angle here, right? So pi over 4. So pi plus pi over 4. Well, in that case, then we've got 4 pi over 4 plus pi over 4, and that gives us 5 pi over 4 there. Okay? So that gives us our second solution here. And if we just quickly consider them, do we have any more solutions for this equation? For this domain here, the answer is no, because my next solution then would be when we add pi, right? Because tan is periodic every pi radians, every 180 degrees. So if I add pi to this here again, that would be 9 pi over 4, and that falls outside of this domain here. So we'd reject that solution. Okay? So for this equation here, x is equal to pi over 4 and 5 pi over 4. Okay? So now moving on to this equation here, so tan x is equal to minus 1. So as we mentioned before, right, x is equal to tan inverse of minus 1. So just use a calculator here, right? But what you should get then is x is equal to minus pi over 4. Okay? Now it's up to you. You can draw another cast diagram here, but I do feel like that's a little bit redundant just based on this cast diagram here. So clearly my next solution here then, again, let's just do that in a different color. Let's do it in orange. That would be pi plus this solution here. So plus minus pi over 4. So what I've got here then is 4 pi over 4 minus pi over 4, and that just gives us 3 pi over 4. Okay, so my next solution here is 3 pi over 4. And again, we just need to consider here if there is any more solutions. So if I just add pi to this here, what would I get? So if I add pi to this, then what do we get here? So add pi to that, so that's 4 pi over 4 plus 3 pi over 4. That gives us 7 pi over 4. And this here does fall within the domain here. So we would also include this solution. And we just check one more time then. So if I add 4 pi over 4 to this here, that would now fall outside of the domain here. Okay. So what this gives us here then is the solutions to this equation. So what I've got then is 3 pi over 4. So 3 pi over 4. And we also have 7 pi over 4. Okay. Now, as we mentioned before, we're clearly not going to include this solution here, right? Because it's less than 0. So we can cross that one off. So in that case then, let's just give the full solution set here. So therefore, x is equal to, so let's try and do this in size here. So we've got pi over 4. So from smallest to largest, so pi over 4. We've got 3 pi over 4. We've got 5 pi over 4. And then finally here, we have 7 pi over 4. Okay. And there we have it. So that gives us the solution then to the very last part of this question, part B. And that gives us the solution to question 2. So to finish with here then, let's have a go now at the very last question, question 3. So for the first part of this question, then part A, what we want to do here is express 9 sin x plus 12 cos x in this harmonic form here. We've got 9 sin x plus 12 cos x. And we want to put it into this form here. So r sine of x plus alpha. So r sine of x plus alpha. Okay. So by using the addition formula here then, r sine of x plus alpha, that is just the same as r sine x cos alpha. So r sine x cos alpha plus r cos x sine alpha. So r cos x sine alpha. Okay. So in that case then, hopefully you can recognize here what we've got is r cos alpha sine x. So r cos alpha, I'll put that in brackets as well. So r cos alpha sine x plus r sine alpha cos x. Okay, and again, let's put that in brackets. So r sine alpha cos x. Like so. Okay. And therefore, by equating coefficients here, what we can see then is r cos alpha is equal to 9. So r cos alpha is equal to 9. And r sine alpha here is equal to 12. So r sine alpha is equal to 12. So therefore, in that case then, what do we do here? Well, don't forget that r is simply Pythagoras here. So we take the square root then of, it's going to be 9 squared plus 12 squared. So 9 squared plus 12 squared. So in that case then, just put this into your calculator here. What we get is the square root of 225, which is just 15. Okay, so r is equal to 15 here. And then for tan alpha, so for tan alpha then, this would be r sine alpha divided by r cos alpha. So in that case then, what we get here is, so r sine alpha, so that's 12 over 9. So 12 over 9 there. And then in that case, if we just want alpha here, just take tan inverse of both sides, right? So alpha is equal to tan inverse of 12 over 9. If you just put this into your calculator here, what you should get then to 3 decimal places is 0.927. Okay. Just notice here as well, right, that alpha is in radians as opposed to degrees. Okay. So 0.927 radians there. So if we just express it in this form here then to finish with, What we've got here then is 9 sine x plus 12 cos x. And this here then is identical to, so it's r sine of x plus alpha. So r is 15. So 15 sine of x plus alpha, where alpha is 0.927. Like so there. And there we have it. So that gives us the solution there to part A. So now for part B then, let's do that over here towards the bottom left. It says, hence find the greatest value of 9 sine x plus 12 cos x all to the power of 3. So 9 sine x plus 12 cos x all to the power of 3. Okay? So to begin with here, let's just consider the maximum value then of 9 sine x plus 12 cos x, or the greatest value. Okay? So the maximum or the greatest value here then of 9 sine x plus 12 cos x, that would be when sine is equal to 1. Okay? So 15 times by 1 here. So what that means then is the greatest value of 9 sine x plus 12 cos x is 15. So 9 sine x plus 12 cos x all to the power of 3. Well, the greatest value of that then is going to be 15 to the power of 3. 15 cubed, right? So just put this here then into your calculator. So 15 cubed. And what we should get here then is 3,375 there. Okay. So that gives us the solution to part B. And as you can see then, we pretty much took up the full screen to answer part A and part B. So let's just quickly pause the video here, clear the screen, and then we can have a go at answering part C. So we've cleared the screen now, so let's have a go then at answering part C here. And before we continue with part C, there is just 2 quick points to make here. So as you can see at the top of the screen here, I have kept the solution from part A. So this is the harmonic form that we obtained in part A. And the reason that I've kept this here is because we will need it to answer part C. So it's there for reference if you haven't already got it. And then what I've done here is I've just made a slight adjustment then in terms of how we present the solutions here for part C. So originally it just said give your answers to 3 decimal places. I've just changed that to significant figures. So not a drastic change, but please do be aware of that because it will change your solutions. Okay. So other than that, we don't need anything else here. So let's just get started then with part C. So for part C then it says solve for x between 0 and 2 pi the following equation. And again, just as we've mentioned here, given our answers to 3 significant figures. So to begin with here then, let's just write down this equation here. We have 9 sine x plus 12 cos x is equal to 7.5. Okay. Now just notice here then, the left-hand side of my equation here is what we started with, right, in part A. When we express this here in part A in this form, in other words, in harmonic form or using the harmonic identities, so in that case, then what we can do here is replace this left-hand side with its harmonic form or its equivalent harmonic form. Okay. So what I've got here then is 15 sine of x plus 0.927. And that is equal to 7.5. Okay. So the next thing that we can do here then is divide both sides by 15. So in that case, then what we get here is sine of x plus 0.927. And that is equal to 7.5 over 15, which is just equal to 1/2. Okay. So now the next thing that we can do here then is take sine inverse of both sides. So if we do that here then on the left-hand side, we just get left with the argument of our trigonometric function. We just get x plus 0.927. And that is equal to sine inverse of 1/2, which is just equal to pi over 6. Okay, hopefully nice and straightforward there. Now, before we do anything here with the 0.927, let's just obtain our remaining solutions here by using a cast diagram. Okay. So with my cast diagram here, doesn't have to be perfect, by the way. Something like this is absolutely fine. So bottom right is cosine, top right is all trig functions, top left is sine. And then bottom left here is tan. Okay. So this solution here corresponds to this quadrant here. And that's this angle here. So that's pi over 6. Okay. Now my next solution then lies in this quadrant here. So this angle here is also pi over 6, but what I want to know here, let's do it in red, is what is the angle that's formed then going from this line here, essentially the x-axis, all the way around until we meet this line here. What is this angle? Well, hopefully then from my cast diagram here, it's clear to see that this would be pi radians, minus then the angle in between here, which is pi over 6. So pi minus pi over 6, which in this case here is just 6 pi over 6 minus pi over 6, and that gives us 5 pi over 6. Okay, so this solution here then, or this angle that's formed then, is 5 pi over 6. So what I've got here is also x plus 0.927 is also equal to 5 pi over 6. Okay. Now, what would happen here then if we subtract 0.927? So just grab a calculator here, right? Because this is for x plus 0.927. So pi over 6 minus 0.927, that gives us a negative solution, right? So it falls outside of the domain here. So we'd reject this solution here. So we'd reject that one. This one here, if we subtract 0.927, so 5 pi over 6 minus 0.927, what does that give us here? So two free significant figures here, what that gives us then? So x then is equal to 1.69. Okay. So do we have any more solutions remaining here? Well, if we just go back to this equation here then, and don't forget that sine is periodic every 360 degrees or 2 pi radians. So in other words then, it just repeats every 360 degrees or 2 pi radians. So what that means then is, let's do that down here. Let's add 2 pi radians to this solution here. Okay, so pi over 6 plus 2 pi. Well, what would that give us here then? So this would be 12 pi over 6 plus pi over 6. That's 13 pi over 6. Okay. So 13 pi over 6. So if you just put that into your calculator here, right, we get 6.806, 784, so on and so on. So your first thought then might be to reject that solution because it falls outside of this domain here. But don't forget, what we also need to do here then is subtract 0.927 from this. So once we do that, it will fall inside the domain here, okay, the domain of valid solutions. What I've also got here then is x plus 0.927 is equal to 13 pi over 6, okay? So what we need to do here then is subtract 0.927 from 13 pi over 6. So if we do that here then, what do we get? So subtract 0.927 and give your answer to three significant figures here. And what we get then is 5.88. So x is equal to 5.88 there. Okay. And there we have it. So there's no more solutions here. If you consider adding 2 pi to, for example, 5 pi over 6 here, we do fall outside of the domain of valid solutions. Okay. So there we have it then. So let's just give these solutions underneath here. So in that case, then x is equal to 1.69 and 5.88 here. Like so there. And there we have it. So that gives us the solution to the very last part of this question, part C. And that actually gives us the solution then to the very last question, question 3. And that brings us to the end then of this video here on exam revision for trigonometry and modelling.